All right, this is going to be another one of those I can walk through lecture notes. These are available on the Google Drive, a completed form, but the one I'm going to work through might have some big gaps where, again, you'll see it completed on the handout, but these gaps are so that I can kind of work through the example and you can see the actual process in addition. So this lecture that we would have had the Monday after we returned from the break was going to be a little digression on pressure. So just to set the stage, remind us where we came from, we were focusing on differentiating between kind of properties of particles in a box and then photons in a box. And we were looking at things like how you quantify number density, the connection of temperature to the average energy, and then the flux of energy and momentum. Energy, or temperature, kind of connects to energy in thermodynamics, where pressure connects to momentum in thermodynamics. So the idea with pressure is, suppose you have a bunch of particles in a box, but I'm going to restrict myself to just one particle that's only moving in one dimension, so it can only move right and left. And we have a wall here, and there's a little section delta A, has some area A. Again, the kind of third dimension is kind of in and out of the page, which I won't bother drawing. And there's some section of area where I want to quantify this thing called pressure, which is typically defined as force per unit area, or the force that's being spread over some area where the pressure or where the force is being exerted, which we call pressure. Because again, you don't really apply a force at a literal point. I push on a ball, I'm pushing across a large chunk of the surface of that ball. I'm standing on the floor right now. My weight, the force mg, is being counteracted by the floor pushing back up. But the floor is pushing back up on me through my feet, where the floor and my feet are in contact. And that is being done over an area equal to the area of my 2 feet. So let us review where we got the definition of pressure. So you have this particle, and it elastically bounces off the wall, which means it returns with the same kinetic energy, no change in v, or the magnitude of v, rather. There is a change in the vector v, of course, because the thing turns around. So if I want to focus on the particle itself, there is a change in momentum that the particle undergoes. Its final momentum minus its initial momentum, which its final momentum looks like it's moving to the left, and its initial momentum is moving to the right. So if I define in my usual way that right and up are the positive directions, then it looks like the final momentum is negative p, and then I subtract the original momentum, which was positive p. And so the overall delta momentum is negative 2 times the original magnitude of the momentum of the particle. That delta p is the delta p of the particle. But of course, by momentum conservation, which really is just another way of saying Newton's third law, that change in momentum here of the particle had to go somewhere. That change then was given to the wall itself. So while the particle had a delta p of negative 2p, the wall had a delta p of 2p. So that is the total momentum that is given to the wall during the single collision. So this is kind of the momentum per collision in 1D. And this occurs over some finite amount of time, delta t. The force, by definition, Newton's second law, is the derivative of momentum with respect to time. I'm kind of doing it with these deltas, so we can write that the force exerted on the wall over that time delta t is the change in the momentum, for the wall, divided by delta t. So this would be plus 2p. So this entire thing is pointing to the right. That makes sense. If I have a particle, smacking the right wall, coming from the left, it makes sense that that wall should feel force moving to the or pointing to the right. So if the force is delta momentum over delta time, and then we can define pressure as that delta F, that force over the area that I'm concerned with. So ultimately, if we want to evaluate pressure, what we really want to do is figure out the change in momentum for a surface of area A in a time delta t. Now, what did we do before? It was more than one, if there's many particles in the box, and again, we stuck with 1D, to help our intuition. So we had half the particles moving to the right and half the particles moving to the left. So the number density, or if there's n total particles, the number density is then n over the volume of this box. And so then half of them, n over 2, is moving to the right, and the other half is moving to the left. If I want to calculate in a time delta t, and they all have the same, some average energy, which we're going to say that they all have the same velocity v. So if we want to calculate the pressure on this chunk of wall, this little area delta A, then we need to know the total momentum that was exchanged with the wall over a time delta t. So that's going to amount to us just counting the number of collisions that happen in a time delta t. And so we can define this volume here, which is particles that are moving to the right and are in this volume are moving such that they will hit the wall in some time delta t. So this length here is v delta t. So a particle that's right on the edge of the box, in time delta t will just make it to hit the wall. Ones that are closer will hit and rebound during that time. So, and if we have a number density, again, the number density is telling us kind of the average number of particles, per kind of unit volume. So that we have this unit volume here that we can think about how many particles live in this volume. And again, remember that this is a 2D area, in and out of the page as well. So you kind of like imagine, a little box or something. So what did we do? So the total momentum exchange was, right, there's n over 2 particles moving to the right, but not all of them live in this little region right here. So we only are focusing on the fraction of the particles in the entire box that live within this little, rectangle area. So then if this is the average in the box, then this gives us, so this is kind of number per volume. This has units of volume, so this entire thing gives units of number. So then this is the total number of particles that will collide with the wall, or the total number of collisions. And then there's 2p momentum exchange per collision. So if you think of this as units of collisions, momentum per collision, this entire thing has units of momentum. And so therefore, notice, conveniently the delta t and delta a are here, so that when I divide them out, I get an expression that doesn't have any of my kind of human-made little variables like these delta t's and delta a's. They all vanish. In the calculus limit, of course, these all become derivatives. So then the pressure ends up being the number density times the velocity times the momentum, which in non-relativistic terms is just n mv squared. That mv squared, looks tantalizingly like kinetic energy, so I'll multiply and divide by 2. And then since all the particles are moving with the same speed, or they all have the same average energy, we can write that the pressure is 2NE, where E is the kind of the average energy per particle. Well, in this case, it is the energy per particle since they all have identical energies. We're here in these next steps, really, we can generalize, right? In general, it's not that they all have the same velocity, but there's going to be some distribution of velocities. So we might also want to be able to talk about some sort of average velocity, right? So I might say that the pressure can be defined as 2N times this average energy. And really then what I should be saying here, and we'll see this later, I'm going to make a little edit. Turns out that's not the average velocity that ends up playing a role here. So if the average of E is the average of the kinetic energy of the particle, then really the average of the average energy connects to 1/2 and the m are constants, connects to an average velocity squared. So the average energy per particle has a deeper connection with the average of the square of the velocity, not the average velocity. We'll come back to that, which might seem a little subtle in a bit. So then, in general, we're going to make kind of go on to this assumption. Then in this case, since we're considering everything in 1D, remember that we had a pretty important result from thermodynamics that we said, in these thermodynamic systems where everything's kind of mixed up and stirred and randomized, the average energy per particle ends up being 1/2 kT times the number of degrees of freedom, which for particles, not molecules, is the number of dimensions the object can move. If you have molecules, you might have rotation and vibrations as well. So in this case, since everything's moving in just 1D, the average energy per particle we would expect to be 1/2 kT, which then when you plug all this in, you get that the pressure goes as nKT, which is the ideal gas law. And this is kind of sketched out in 1D, but then you do this more carefully, and it also holds in 3D as well. So that's, again, an idea of just build our understanding of what is pressure. Things are hitting things. Right, collisions are important for momentum transfer. And this is also how kind of energy is distributed amongst the particles. If they all start with the average energy, then they all have an identical energy, but it does not stay that way. As they run into each other, they might hit each other head on, or they might end up hitting each other kind of at a glancing angle. Or a particle might hit, if a particle, like the examples we did above, if a particle hits the side of the wall kind of face on, then it rebounds with just its entire velocity vector is just with an overall negative sign. Which makes sense, it's an elastic collision, all that good stuff. But then if a particle hits it kind of edge, at an angle, it's still an elastic collision, so the total kinetic energy can't change, but in this case, Vx gets, an overall negative sign. But then Vy is not changed at all, which is different in this case, compared to kind of the 1D example where the entire velocity vector changed. So that means that if everything starts with exactly the same thing, that, through all these interactions, the distribution of energies can become more than just a Dirac delta function, right? A spike at one particular value. So while we talked before about how the average energy per particle is going to be 3/2 kT for particles moving in a 3D box, and again, this is how we define temperature. We can use this as a way to define temperature, essentially as a measure of the kinetic energy of the particles. But as they hit each other and bounce off walls and all that stuff, their velocities are going to change, their kinetic energies are going to change. So again, we do not expect that all the particles' energies will be exactly 3/2 kT, but we are very likely to find that it is going to be distributed nearby or about 3/2 kT. We should be able to justify this, because if we claim the average energy per particle is 3/2 kT, and then after things hit around, bounce off one another, right, that stops being true, then we don't have a very good theory. Of course, it turns out, everything is going to be fine. But that's something to keep in mind. As I state these things, we have to be able to, corroborate them with experiment or derivation. Let's do a quick example first. Let's estimate the number density of air in this room, or in whatever room you're in right now. I assume you're not watching this on the top of a mountain or at the bottom of the ocean. So let's estimate the number density of air in the room. It also gives us an opportunity to talk about the units of pressure. So P equals nKT, the physics version of the ideal gas law. Again, remember, you might, from chemistry, be more familiar with kind of n moles times the gas constant times T, which can be converted from one to another, right? If you want to convert number of moles to number density, you can do so. That pops out in Avogadro's number, and it turns out, and there's a volume, right? I guess they write it as PV equals nKT. What are chemists doing? So you can kind of convert between the two, essentially, to go from this to this, right? If you divide by n, you divide by V, looks like you have a number per volume, But then to turn this into just a number instead of number of moles, Avogadro's number pops out, and then Avogadro's number times this gas constant is just K. And then the total number divided by the volume is the number density. All right, so we want this, that's a constant. The temperature in this room, to use nice round numbers, do this order of magnitude, we'll call it 300 Kelvin. It's not quite that hot in this room. And then the pressure, you might remember from a chemistry course or something you did in high school, that usually at sea level, we talk about the pressure being 1 atmosphere or 1 atmospheric pressure or 1 atm. That is not the MKS unit, but this turns out to be about 10 to the 5 pascals. And that is the MKS unit. So again, if pressure is force per area, then that's going to be a pascal. That's going to be Newton per meter squared. This also is equivalent to another unit of pressure you might see. It's about 15 psi, or pounds per square inch, which is another way pressure can be quantified. So then it seems like we can now write P in MKS. Everything's in MKS. We're good to go. So then it looks like N air is going to be P over KT. So then that looks like it's going to be 10 to the 5. That's 5. Boltzmann's constant, which in MKS is, we'll call it order of magnitude 10 to the negative 23. 300 Kelvin, 3 times 10 to the 2. And let's see. So then 2, that becomes a 3. I could pull one of those 10s out and divide by the 3. So then if that's a 2, then that pops out a 3 on top. 10 divided by 3, we'll call 3. And then I'll move the 10 to the negative 23 upstairs. So then it looks like that is 3 times 10 to the 25. And what is the unit? It's going to be number per volume, so number per meter cubed. So 3 times 10 to the 25 particles in a cubic meter. Or if I want to convert to centimeters, because I can have an easier time envisioning a cubic centimeter. Well, going from meter to centimeter is a factor of 100, but then this thing is being cubed, so I have to essentially do a unit conversion 3 times to turn this into centimeters cubed. I also know a centimeter is smaller, so just by intuition, I know that this number should go down. I can fit fewer particles in a smaller box. So factor of 10 to the 2, but I cube it, factor of 10 to the 6, and it's decreasing, so then this becomes 3 times 10 to the 19 cubic centimeters. So 10 to the negative 19 particles per cubic centimeter. Right? Again, thinking of like, my pinky. That's a lot of stuff. Let's, in contrast, all right, you go to the average kind of a location in the galaxy, kind of the average number density in the Milky Way, which ends up being part of the warm neutral medium, I believe. It's about 1 particle per cubic centimeter. So 19 orders of magnitude more tenuous. Space is not a vacuum, but it is pretty damn close. Now, have we actually ever achieved, we have these vacuum chambers on Earth. What has been our kind of best vacuum chamber that we've created? It's very hard to create a vacuum. To get all those individual, all those tiny little particles out can be very challenging. I think one of the best that we've done is at CERN, part of the Large Hadron Collider, where they can get pressures down from 1 atm, or 10 to the 5 pascals, down to about 10 to the negative 3 atm. So there they can decrease it by an order of magnitude, 13 orders of magnitude, which is not 19, but 13 is still pretty high. So then that would imply kind of the number density in these kind of CERN vacuum chamber. It's probably something on the order of 3 times 10 to the 6 per cubic centimeter. So there's still a million particles, but that is, so many dramatic orders of magnitude fewer that it behaves. Air resistance from a million particles ends up being fairly negligible. So it operates pretty well like a vacuum. Now, a concern you might have, I kind of was wondering this, when you are still kind of developing an intuition for the numbers here, right? We just said, I'll copy it over, that N air is about 10 to the, let's go back to MKS, 25. I'll drop the 3. All right, so we're doing order of magnitude, kind of 10 to the 25 per meter cubed. And then air is, predominantly N2, O2, which I expect will have sizes, on order. If the hydrogen atom is 1/2 times 10 to the negative 10, order of magnitude, I probably expect these to be on order of 10 to the negative 10 meters. So I could ask, can these particles actually fit in this volume? Are they on top of one another, or is there still plenty of room left for even more particles? So I can just ask the question, does air fit? So, and obviously, yes, of course it does. So if I look at the volume that's taken up by N2 and O2, so volume of, I guess a volume of air. If I assume they're not overlapping one another, then I might expect that the volume of an individual one is probably going to go like 10 to the negative 10 meters cubed. Right now, it's a little cubic box for each particle. And is there enough room in this big meter by 1 meter box for all these little boxes? And of course, then this volume is 10 to the negative 30 per meter cubed. And then how many particles are there? There's 10 to the 25 particles, so there's 10 to the 25 of these little boxes. But notice that this is only a volume of 10 to the negative 5 meters per meter cubed. So the kind of V air over meter cubed is 1/100,000. So plenty of room still in the box to put other things in if we want. So we could ask ourselves, you've probably heard the expression, that air is moving at hundreds of meters per second, which is pretty fast. But an individual particle doesn't really get anywhere because it hits other particles, almost immediately. So we could ask ourselves, can we estimate what is the average separation of particles in this box, or in the air in this room? What do I need to know in order to make in order to quantify at least order of magnitude? What is the average separation, between individual particles? This ends up that this information is perfectly well encoded in the number density. Since the number density is telling you the average number of particles per volume or per unit volume, you can kind of flip it on its head to give you kind of a sense of the volume that is taken up per particle. And therefore, you can use that to make an estimate of the average separation. So I have these two little pictures that you can use here. Right? And the case of the top box is a low number density. Right? If this is 10 meters cubed, right, then there's 5 particles per 10 meters cubed, or 1/2 per meter cubed. So if I could imagine, starting at a particle and just drawing bigger and bigger circles until I start to touch, one or two additional particles, and then use that to maybe estimate kind of the average separation, the radii of these little circles. So you can see I can draw circles, kind of on order this size before I start running into other particles. Versus this box where the number density is much higher, and I have to, and I can't draw quite as big as circles before I start running into into other particles. So, what you can do, and if you might think, is this related to something like the mean free path that you've heard? Maybe that's a phrase you've heard. Absolutely. When you're dealing with collisions, this is very much related to that. Right. So, to kind of work via example, right? If I say that n is 6, per unit volume, so that maybe there's a box, there's six objects per unit volume. Then I could ask, I could think of that the entire kind of meter, if I think of a box that is 1 meter by 1 meter by 1 meter, and there's 6 objects in it, blop, 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 blop. You could think of partitioning this box into 6 compartments. Something like that. I don't know something. And then what is the typical volume of that box? And then if you know the volume, I could take the cube root and maybe say something about a distance. So, and again, then you could think of if I had, instead, if n was 600 per meter cubed, I'd be making much smaller compartments. So, let me move this over. So if n equals 6 per meter cubed, then that's on average, there are 6 particles, per meter cubed. Or you might think that each particle, takes up a volume of about 1/6 of meter cubed. So then each compartment, and again, remember, that's not saying that the particle is that big. It's saying that, if you have kind of on it, if you have 6 particles and you want to break this volume into 6 kind of equal volume compartments that fill up the 1 meter cubed, then each one of those particles gets a compartment that's 1/6 of a meter cubed. Each compartment. Let's see. So each compartment has a, you can think of has a width or a length or a side length of roughly the cube root of this 1/6 m cubed, or the cube root of 1/6, and then the cube root cancels the meter cubed, so whatever that number is. Let's see here, 1 divided by about 0.55, so if that matters. And you could use that as kind of an average separation between particles. Now, if we think about what we did, we started with this number density, and then we thought of breaking the unit volume into an equal number of compartments. So the 6 became kind of a 1/6, and the meter to the -3 became meter cubed. Well, it looks like we just took the reciprocal of the number density, and that is exactly what we did. And then we took the cube root of it. So you can define kind of the average separation if you want to estimate it, you can estimate it as the you take the number density, you do 1 over the number density, and then you take the cube root. So then this becomes just n to the -1/3. Right, the negative 1 makes it 1 over, and then I've taken the cube root. So, for air, we said that it is, the number density was 3 times 10 to the 25. For some reason I put the 3 back. Meters to the negative meters to the negative 3. Then I'm going to take the negative cube root. Or I'm sorry, the 1, I'm going to do 1 over the cube root, or raise this all to the negative 1/3 power. Then the exponent distributes, so then it's going to be 3 to the negative 1/3 times 10 to the 25 raised to this power, so 10 to the negative 25 divided by 3. And then the negative 3 and the negative 1/3 cancel, and this becomes units of meters, as it should. All right, so 3 to the negative 1/3, more or less, a few. So when I plug all this in, I ultimately get about 3 times 10 to the negative 9 meters. Or, what this says is that the average separation for air is, a few nanometers, which is bigger than the size of the atom. That's good. So there's no kind of contradictions there. But this essentially is telling us that the particles aren't going to really go anywhere, even if they're moving pretty fast. Oh, I recopied what's there. Fine. So this is just this. So then we can also ask about the speeds. Again, speeds we can get from the thermodynamic relationship. If the average energy per particle is the number of, that should be degrees of freedom, not dimensions. Oh, I guess, yeah, we're thinking of atomic, we're not considering rotation vibration, so, the number of dimensions it can move in, and 1/2 kT, so that's fine. Then what is this saying? If I want to be a little bit more quantitative about this. So then that is saying, this is saying that the average kinetic energy is equal to 1/2 kT times the number of degrees of freedom. And the average implies, like I said on the first page, that when I take the average of the kinetic energy, really I'm taking the average, right, I'm taking the average of 1/2. Yeah, that's the same. That's just equal to half, average of m. If I treat all the particles as having the same mass, that's the same. So then really this average is over v squared. And that's equal to 1/2 kT times the degrees of freedom. So I could solve for the velocity, but again, I can't really solve for the velocity because it's buried within this average. But I know this thing here has units of velocity squared. So if I want something that has units of velocity, I might imagine taking the square root of that thing. Then that has units of velocity. So then if you solve for the square root of this average, that's what's called the root mean squared velocity. Right, you're taking the root of the mean of the square values of the velocity. And that's equal to the square root of number of degrees of freedom, kT, over the mass of the particle. So, if you were setting this up in a simulation or in some sort of, experiment, if you wanted to say that the particles in the box had a particular temperature, what you would want to do, and they're all identical particles, what you would want to do is set it up such that the root mean square velocity is equal to this. That would then be saying that the average energy per particle is equal to this, which again is how we define temperature. So, now you might say, this is messier than I want it to be. It's not too bad, actually. There's 3 velocities you'll typically see kind of, tossed around. There's this root mean squared velocity, which is, again, the square root of the mean of the square values. So I add up all the square values, divide by the number there is, right? That looks like a mean, and take the square root. That, of course, is not the same always as the just average velocity of the particle, which is then you add up all the velocities and you divide by the number of particles. Nor is that the same thing as what I might call v mode, which is the most likely speed. And what is the speed, which speed has the highest probability of a particle having, amongst all the possible velocities it could have. The good news is it turns out these all are very, very similar in order of magnitude. And their utility depends on the context. For example, when we did this little derivation here, right, the root mean squared velocity became the relevant thing to talk about because kinetic energies have velocity squareds. So when we're talking about average energies, that then corresponds to us talking about average, root mean squareds, rather. For other contexts, might make sense that the most probable or the average velocity is the velocity you're talking about, if you want to be specific. So, let's see if we can actually now try to write down or display what this distribution is. Because again, I could set it up such that, maybe I set it up such that, the particles in a box all start with the exact same velocity, such that this is satisfied, saying that the average energy per particle is, or each particle's energy is exactly equal to this, corresponding to a particular temperature. And as they bounce around and bounce off each other, right, I expect that, a distribution of velocities will form. And of course, deriving that is beyond the scope of, this course. We'll leave that to thermodynamics. But we can talk a little bit about how you get about it, and then look at the result itself. Obviously, this distribution should depend on the average energy, or the temperature. If I have particles that have barely energy at all, I'm going to expect a distribution of, velocities are essentially all very close to zero. Versus if I have a very hot gas, I might expect the average energy to be large. I might expect the kind of typical velocities to be something that increase with temperature. But then what does the distribution look like? Can you still have particles that are essentially not moving when you have a very large temperature? Of course. So in order to derive this, it uses what is probably kind of the result, or one of the major results of classical statistical mechanics. That when you're doing thermodynamics and statistical mechanics, again, you're not doing F equals ma to every particle, but you're looking in a statistical sense of what's going on. And what Maxwell-Boltzmann was able to find and conclude in his studies of StatMech, essentially why everything has his name attached to it in StatMech, is that he was thinking, again, when you're doing things statistically, you're thinking about you're thinking more probabilistically. And this is even before quantum mechanics, right? You're thinking kind of probabilistically about, I pick a random particle in the box, what's the probability of its velocity being, x versus y or whatever. So he concluded and was able to show that, this is kind of a major result, that when you're talking about energies, the probability that you're going to find a particle with a particular energy, E, and remember, E is going to be the kinetic energy here, so write that off to the side as a reminder. All right, so this E is going to be 1/2 mv squared, at least for this discussion. Now, the probability of finding a particle with a particular energy E is proportional to this exponential, E, Euler E to the negative energy over kT. That's what's called the Boltzmann factor. So what this says is that the probability, we can use this margin here in the bottom, right? If, maybe if you want to give some numbers, suppose kT is such that, again, I just want to play with the math. Maybe kT is such that it's equal to, 2, technically be 2 joules. So then, if you have a particle that has a kinetic energy of 1/2 joule, right, then that's e to the negative 1/2 over 2, which is, gosh, I'm starting to forget how to, where everything is on this calculator. Negative 1/2 divided by 2. So that's about, 0.77. Compared to if you had a, so this is E equals 1/2. So then if E instead equals 4, then you have e to the negative 4 divided by 2, or e to the negative 2, which then is going to be much, much smaller. e to the negative 4/2, which is about 0.13. So, just remembering how the exponential works. The exponential, if I write it as negative, well, since we're dealing with energies, we can write kind of E over E naught, right? Call KT E naught. So then when, that looks then like something that drops down and exponentially, drops to 0. But essentially you don't get this drop down until epsilon is comparable to epsilon naught. Then you get kind of, a factor of E drop down. And then when epsilon is 2 epsilon naught, you get another factor of, that this drops down. And the thing starts to drop dramatically after that. You essentially lose about 36%, every factor of E, Euler E. But if you have energies that are really, really small compared to E naught, then that's essentially, if you have like E to the 10 to the negative 3/2. Well, the numerator is essentially 0, right? So it's essentially the same thing as E to the 0, which is just 1. So what this says, kind of a sloppy margin stuff there. What that says is that since the probability depends on this exponential, which drops down as epsilon becomes comparable and greater than KT, that means the higher the energy, the less likely it is that you will find the particle with that energy. Higher energies are less likely, you're more likely to see things with lower energies. And again, it kind of starts to really drop down when epsilon exceeds KT. So what we would expect is that epsilons kind of around and less than KT are probably the ones we're going to find. Because something could stay perfectly still, but then it's likely that something's going to come around and hit it, in pretty short order. So you're probably not going to stay with a very low velocity, for very long. So we expect probably that the average energies are going to probably be on order KT by this argument, which is again kind of what we're saying up here. And then collisions start to collide, with each other, and an overall distribution might start to take shape. Now, to calculate the distribution itself, there's an additional challenge here that, when you're calculating these probabilities, the probability that a particle has some energy E, or epsilon, there's the Boltzmann factor that you have to take into account. But you also just take into account the degeneracy of the state. So if I'm thinking about a particle that has a particular energy, there is likely multiple ways that particle can have that total energy. Think of just kinetic energy. Come on. If epsilon is the kinetic energy, right, really that's 1/2 m, the magnitude of the velocity vector squared. And I can draw many vectors that are different from one another, but they're all the same length, so they all have the same magnitude. And in this case, they would all, if the particle had any of these vectors as its velocity, they would all evaluate to having the same energy. So there are multiple ways that a particle could, have some sort of velocity and some sort of position in the box and have the right energy. So essentially what you also have to do is take into account you have to do some accounting of the number of states, that has this particular energy, multiplied by this Boltzmann factor. And then you can do all that work, and it's actually not terribly hard to derive, but again, it would take, probably 40 minutes for me to do it, so we're not going to do it. But you ultimately can get a distribution that emerges, which is called the Maxwell-Boltzmann distribution. And just to see this in action before we get into the math, let's look at a couple of simulations I made to demonstrate this. Okay, but before actually we do the simulations, let me just sketch some of the mathematical results and talk a little bit about what it means to be a distribution function. So this Maxwell-Boltzmann distribution function, turns out, we're going to look at it in 2D because the simulations are all in 2D, but I'll also write down the results for 3D. So when the number of dimensions is 2, we're going to talk about this distribution function, which I'm going to write as f sub v, and it's a function of v and t. It's going to give a distribution across velocities for a given t. This ends up being proportional to v times the Boltzmann factor. There's an exponential of negative m v squared over 2kt. And then when the number of dimensions is 3, this distribution function ends up being instead proportional to v squared times the Boltzmann factor. It actually turns out in general that it's v raised to the number of dimensions minus 1 multiplied by the Boltzmann factor. If you had maybe a 1D or a 10-dimensional, space. So again, we have these proportionalities here, but this does give me a distribution, right? If I just said the proportionality constant was 1, I could plot this. Now, a distribution function, again, think this is all coming out of statistical mechanics. We're thinking statistically about this, right? It might, this distribution function essentially is telling us on average, what fraction of the particles in the box are at a particular velocity. Or if I were to randomly pick a particle, what's the probability that it would have a particular velocity? So you can think of it in a couple different ways, depending on if you want to think of this in terms of probabilities, or if you want to think of this in terms of kind of number or fraction or whatnot. Let's think of it in terms of probability. So this can be defined. So essentially, what since it's proportional, this is the same thing as if I write f sub v, vt is equal to some constant a, v, number of dimensions minus 1 times the Boltzmann factor. And so this is my Maxwell-Boltzmann distribution for some constant a. And we can define this to be a probability distribution function by saying that we define it such that f sub v of v comma t dv, if I integrate this from v0 to v1, we could define that to be the probability that a particle has a particular speed, right? Has a speed in the range v0 to v1. So that the integral of this function can relate to probabilities. So the integral from v0 to v1 is saying that's the probability that a particle would have a particular speed, some speed that's between v0, or it could be equal to v0, and v1. Now, it has to be this way. Essentially, in the continuum limit, it has to be this way because of some other kind of assumptions that are being made here, where if there's an infinite number of possible velocities, then the probability of any individual velocity is technically 0. So you can't really talk about the probability of individual velocities, but you can talk about the probability of a range of velocities. You don't have to worry too much about that, but just if you want to know some of the details. Now, probability, probabilities, you have some familiarity with this. Probabilities. Well, that doesn't look any nicer. This allows us to then figure out what the constant a is. So there's what's called the normalization factor, where probabilities are numbers that range between 0 and 1, where 0 means it's impossible, 1 means it's inevitable. So I could ask, what is the integral from 0 to infinity of, oops, I forgot the dv, of this distribution function dv? Well, that's essentially saying that's the probability that the particle has any velocity or any speed, right, since we're just looking at the magnitudes. So, of course, that better equal 1, right? The probability that a particle has any of the infinitely possible speeds. So this is what's called the normalization condition. which allows you to then figure out the value of A. What value of A will make it so that when I compute the area under the curve between 0 and infinity, I get that that area is exactly 1, which then is kind of the characteristic of what is a probability distribution function. So let me write down what A, well, is it down here? It is not. So then, for example, in 2D, in 2D, the normalization condition would say, do the integral from 0 to infinity of A times V times e to the negative mv squared over 2kt dv, and I'm going to set that equal to 1 by that condition. Well, the A is a constant. It can pop out, and this actually isn't a bad integral at all, because you have a V, and you have this V squared thing, but I could do a U substitution and integrate that, no problem. You should not have an issue with that. The A just pops out, so then you ultimately can solve for A and should find that it is the square root of 2 over pi multiplied by m over kt, all to the, oops, sorry, I just wrote down the answer for 3D. Ignore that. The answer ends up just being m over kt. Such that, again, so that if you write in 2D, A we just said is m over kt, and this is all being multiplied by v, and this is all being multiplied by mv squared over 2kt, that this is, and again, the m, the kt, those are all constants, that is a distribution function, and where if I compute the area under the entire thing, it has an area equal to 1. So if I were to plot this, and we'll do the 2D one here. Actually, let me write down the answer for 3D first. So 3D, you can do the same thing. And then it turns out that A in 3D is what I was starting to write down, square root of 2 over pi. And then there's the m over kt, but it's being raised to the 3/2 power. And the general shape is more or less the same. So if I were to plot this, it might look something kind of like this. So it, of course, has to go to 0 at 0, right? You can have negative speeds. But then it rises up. There's some well-defined peak, and then it starts to come down. And there might be a long extended tail. So this might be, and then let's see if we can define some things. This kind of peak, this maximum value, pretty easy to derive. You can try deriving it yourself, right? That's what I was calling V mode, because it is connected to the highest likelihood. This f is not a probability itself, but is a probability distribution function, such that when you do integrals of it, that is a probability. But f itself is not a probability, so don't think of it that way. But the larger f is, then when you do the integral, right, which connects to area under the curve, there's going to be a higher probability that your velocity is, say, in this range compared to if it's in this range. So since it peaks here, that is connected to kind of V mode. Then it turns out that when you do the average velocity, it ends up being just a little bit ahead of it, the average velocity. And then when you do the root mean square velocity, it's just a little bit ahead of that. So again, they're all very similar, right? And that's vRMS. They're all more or less the same, and I think I give what they are beneath. Yeah, right there. As a function of dimension, right? So, depends on the dimension for these two, and this I couldn't figure out a fancy way to do it as one formula. So for 2D, it's that times this, and for 3D, it's this times this. Right, essentially, you can notice that this has units of velocity, so that essentially establishes the unit. And then these are just kind of numbers, coefficients, that just pop out with the math. So, again, thinking of this in terms of probabilities or likelihoods, this is saying that as the particles kind of bounce around and stir up, They might not all have the exact same velocity at the end of the day, but I might expect this is going to be the distribution we want to hope emerges. If it does, pat ourselves on the back. Well, pat Boltzmann and Maxwell on the back, and then use it to our delight. But what does this function look like? I drew it for one particular case here. So again, the way that this has been drawn, the axis, notice, is v. Oh, I switched to blue. So essentially, this is very similar to the thermal radiation spectra we had, where T essentially is a parameter. In order for me to plot this function, assuming I know m and I know k, I have to also have some value of t that I plug in. Then it depends only on velocity, and I can plot it as a function of velocity. For a different value of t, or a different value of m, right, I would get a different curve. So to give you kind of two examples, let's see, I guess this plot down here kind of reproduced that plot. So let's do this. Let's give ourselves some more axes. Right, so there's v. So, just to give you an example, right? So in the case here, where the velocities are kind of, crammed over towards the left, this is the curve you would get, for heavy particles, also for cold particles. So when the temperature is low or the mass is high, the curve tends to move to the left. And as long as it has this coefficient out front, the area under the entire thing is always unity. In contrast, if you have light elements or a hot gas, it spreads out a little bit more. So in that case, then this might be kind of light, not radiation light, low mass light, and hot. And again, the fact that it goes down, that's okay, because again, what's retained is that the area under the entire thing is 1. But then this is essentially saying, the probability of any kind of little range of velocities is lower compared to, say, when it was heavy and cold, because this thing spreads out a lot more. There's a larger kind of overall range of velocities that become possible compared to when it's cold. Because you can then go in the extreme limit, right? Let temperature go to 0. Right, then this thing better cram, right up against the axis. Okay, I think we are ready now to look at some simulations, which I think are kind of fun. So let's see. So they're GIFs, so I'll play them in a browser. So first thing we're going to do, let's just start with a simple example of I have 30 particles in a box, and I'm just going to let them move around. I guess the problem with GIFs is I have no control over their playback. Oh well. So in this case, maybe let me open up a frame. So if we look at the first frame of the simulation, you have balls bouncing around, and they're going to bounce elastically, so energy and momentums are always going to be conserved. But I've set it up such that every particle has the exact same speed, which then corresponds to a particular root mean square speed, such that there's a particular temperature in the box. So I've set up the box to have a particular temperature. And there's some velocity, v0, let's not worry about numbers, that all the particles have at first. So the color of the balls will connect to their speeds. So then, as they start to move around and bounce around, you'll notice that their velocities change. Right? The directions are changing, and then the overall speeds are changing as well. You have particles that are moving very, very slow, and then they kind of bounce off one another. But then you have some particles that are moving faster than they were, compared to the average speed that they all started with. And so you can look and figure out that, if energy is being conserved, the total energy in the box isn't changing, so the average energy per particle is still exactly the same. But you notice that the velocities or the speeds have a distribution. There are some that are smaller than v0, some that are higher than v0, and we want to be now more quantitative about what that distribution looks like. Next one we're going to do is instead of 30 particles, right, because you notice with this simulation, there aren't that many collisions going on. And if I were to look at a distribution, there's not really enough particles to see a nice distribution. So let's have 600 particles. So again, the thing on the left is going to be exactly as before. Oops, this is the wrong one. And that's the wrong one. Okay, where the hell is my simulation? 32. Oh, horizontally. Okay, so sorry, I lied. 200 particles. So 200 particles are going to be bouncing around. And again, I've started them all off with the same exact energy. That corresponds to a particular root mean square velocity. That corresponds to a particular temperature. Again, don't worry about the numbers. So what's now going to be on the right is a histogram that's going to show the distribution of these speeds. So at the beginning here, they all have the exact same speed. So the histogram is very boring. It's a single bar. Essentially, everything is just in this bin, and all the other bins are empty. And I've normalized it such that the area under all the bins is equal to 1. So essentially, the area of this one rectangle is equal to 1. It has a height of like 7.5, and it turns out its width will be about 1 over 7.5. Now, as the particles start to collide with one another and hit the walls and whatnot, just to give you a couple frames forward, their speeds are going to change, and there's going to be some that are now slower, some that are faster, and there's going to be an overall distribution that might start to take shape, or we hope does. That is going to be what this curve represents. So this curve represents the Maxwell-Boltzmann distribution, and let's see, as the simulation runs forward, does the distribution tend to be what we think it should be? All right, so here we go. I'm zooming in, which is why that thing kind of dropped down. And look at that. Look at all, it's still a little noisy. So as it drops down, there are fast particles, there are slow particles. It seems like there's a distribution that is starting to kind of match that Maxwell-Boltzmann distribution. They all had this velocity to start with, but then it seems like these speeds are more probable at the end of the day. And there are some that are out here, but not that many, which is why those bins are smaller. And again, the heights are adjusted so that the area is equal to 1. The area under all of them, just as in the area under this curve is equal to 1. All right, so seems like we're on our way. This was 200 particles. Let's try 1,000 particles. So 1,000 particles, and let's see what distribution emerges. So, okay, it drops down dramatically at first. And there's still noise, but look at that. That's pretty dang good in terms of the distribution that these particles end up having. And it's set up, very, very quickly. The simulation time is kind of one crossing time of the box, so that if the particles never hit each other, it would be the time it takes one of those particles to go from the left to the right. And well before that, all these collisions, right? There's so many collisions that are happening that the distribution takes on this Maxwell-Boltzmann distribution. And again, I'm not hard coding that in. I'm just, all that, I am letting them do is they move in straight lines until they hit a wall or another particle. And they all have the same mass and some arbitrary radius. I guess, a radius I set equal to 5 times 10 to the negative 3 times the length of the box. So that's pretty cool. And in all of these simulations that I showed, they were set up to have the exact same temperature. And so you notice that as the distribution kind of evolves, what happens is that they all kind of end up matching the same Maxwell-Boltzmann distribution at the end of the day. To show you what I mean by that, let's take a look at two different kinds of simulations. So here's going to be a case of 600 particles bouncing around. In this particular simulation, I've set it up so that they had a root mean squared velocity that had this value, right? So that corresponds to a particular temperature. So that's going to be the cold case. This is the cold case. So then if they all start with an energy given by this velocity, then the distribution ends up being kind of what I would have predicted from this black curve. The next simulation I'm going to do is the same setup, but they're all, instead of having this velocity, they're all going to start with this velocity. So they're going to start with an overall higher average energy, which should correspond to a higher temperature. And those particles should end up following this red distribution instead. Let's see if that's the case. So there you go. Distribution drops down. You can look at the simulation on the left, right? They're whizzing around a lot more compared to the other simulation. So I think it's still running. Yeah, see it kind of languidly moving compared to that. And if you look at the distribution, it does take on a shape that looks more like the red curve than the black curve. So it does seem like we're encoding kind of, the relevant physics here. Kind of fun. Then I was really kind of curious of, we set up this thought experiment by saying, like, I have this box of particles and I inject energy into the box. And the way I've been doing it is that I've been giving every particle the same energy, so that there's a well-defined average energy. You could imagine I could do something a little sillier, because if each particle has the same average, let's actually go back to this one. Right, 1,000 particles, they all started with the same energy. So the total energy in the box is then, of course, the energy per particle times 1,000. This kind of starting energy. You could imagine another kind of extreme where I start all the particles in the box as having no energy at all except one particle, which I give that one particle all the energy. Right, so 1,000 times, this average we're seeing here. That's what this simulation is going to show. So there's 1,000 particles. You can't really see the color, but it's one of these over here. Actually, I can just, yeah. So that one right there. That particle is starting with all the energy in the box. Everything else is stationary, which you can notice that this histogram bin, which includes v equals 0. Most of the particles live there, and then there's one particle that's off the plot that has all the energy, the same total energy as all the particles added together in this simulation. So that one particle, of course, then starts off with an extreme energy, and as it goes on, it then crashes into other particles, and let's see what happens. So again, one particle moving, with a blast of total energy. Is the overall distribution going to be the same? Because technically, there's the same amount of energy in that box as the one simulation that I'm showing right now, where they all kind of have an average energy to start with. Here we go. Whoa. And eventually, look at that, same distribution at the end of the day. Once they all kind of stir up and things become thermalized or randomized, all that energy gets spread out in such a way that you get this Maxwell-Boltzmann distribution, which is pretty cool. You can also notice kind of things like pressure fronts, right? Notice that kind of all the particles kind of bunch down here at the bottom for a while before spreading back out. Essentially, you have a high pressure area and a low pressure area, and so you get some sort of bulk motion, but then they eventually spread back out. Kind of cool. All right. So that's kind of cool because it shows that kind of the things we're thinking about really do kind of manifest themselves, even with these kind of very simple simulations. So that's the bulk of it. There's kind of, let's see, I think two more things I wanted to talk about. That one of them is related to the extension, and I think they are mostly just quick examples. So this shouldn't take too long at all. So let's go back to the ideal gas law and talk a little bit about that. So we, of course, write it as P equals NKT. Sometimes it is more useful to talk about the mass density instead of the number density. Right? So this is in terms of number densities. That is how pressure is defined. Remember, it's from collisions, right? Individual objects running into things. But sometimes it is more useful to quantify things based on the mass density, kilograms per meter cubed, compared to the number density. So In the case where, now if we think of units, right, the number density is number per volume, the mass density is mass per volume. So really what this mass density is, it's connected to the number density, but then each particle itself has a particular mass. So the way we'll write this is if each particle, let's take the simple case of everything in the box is identical, right? It's all hydrogen or it's all lithium or whatever. If each particle in the box has a mass equal to its atomic number times the mass of the proton, I won't worry about the proton-neutron having slightly different masses, right? So for hydrogen, A is 1. For helium, A is 4 because there's 2 protons and 2 neutrons in the nucleus, and the electrons don't really contribute much. So if each particle has a mass equal to A MP, then the mass density is just the mass per particle times the number density. So as a result, you can write the ideal gas law also as rho kT over kind of AMP if it's all one species. It's all the same element or ion or molecule or whatnot. But then what do you do if it's mixed? Rarely is it a homogeneous composition, right? If you have some heterogeneous composition, what do you do? Right, and we could motivate this with an example. The Earth's atmosphere. Earth atmosphere. If you look up the composition of Earth's atmosphere, you will hear it often explained as 78% N2, and then 22% kind of O2 by mass. And yet there are other elements, of course, but I'm rounding just to make this simple. So by mass, and the fact that it says by mass is key, because you could say by number as well. It's a different statement to say that 78% of the particles in this room are N2 compared to 78% of the mass of particles in this room are N2. So what is often done is that you can talk about the mass fractions. So we can define mass fractions as the fraction of the total mass. So in this case, N2 has a mass fraction of 0.78, and O2 has a mass fraction of 0.22. And this is defined in such a way such that, let me give these, see, what should I use? I'll use capital X, for the next example I'm going to use. So we'll have capital X sub N and capital X sub O as the mass fractions. So that if there is some sort of total mass in the box that says that X sub N times M total equals the total mass that's in nitrogen. X sub O, M total, is then equal to the total mass that's in oxygen. And again, usually we don't talk about the masses, but instead we talk about the densities. But if I divide these two equations by the volume, then that says that the mass fraction of N times the kind of total density is equal to the density for N2. And XO times the total density is equal to the density for O, or O2, where rho total is just the sum of the two. That's all this is saying. Nothing too sophisticated yet. So where this can be helpful is when you try to use this and employ this in the ideal gas law. So let's think of this. If I were to write down the pressure of air, that would then be an NKT, right? The definition of pressure, NKT. So that would be N total times KT. Where I've assumed that, they've kind of bombarded each other enough that, all the nitrogen and the oxygens have kind of come into some sort of equilibrium, thermal equilibrium, so that I can just talk about one temperature. Now, this N total I could think of as the same thing as if I wrote N nitrogen KT plus N oxygen KT. And from there, I might want to talk about, I can't bring in mass fractions or anything like that yet, because that's those connected densities or mass densities. So I could write this as, I could write the number density in terms of the mass density of nitrogen, KT. But then, let's see, where did I write this down before? Yeah, if you look up here, essentially I'm using this sort of expression where then the number density is the mass density divided by that expression for each particular species. So then for nitrogen, nitrogen, or N2 rather, I think it was 28. I think it's 14 per N. So then it's 28 times the mass of the proton. And then for rho oxygen, KT, and then it's 16 per oxygen, so then 32 for O2 times the mass of the proton. All right, what has this gained us? We haven't quite gotten it to look something like, it would be nice, I would hope, that when we wrote down the ideal gas law here and wrote it as kind of rho KT over some sort of mass per particle. I kind of have that here, but I have it as two terms. I could write this in terms of rho total using the mass fractions, where then P air, I could replace rho nitrogen with X sub n rho total KT over 28 mass of the proton plus the mass fraction of O rho total KT over 32 mass of the proton. Or I can do some factoring. It looks like then I get X sub n over 28 mass of the proton plus X sub O over 32 times the mass of the proton. And that's all being multiplied by rho total KT, and that's it. Actually, I'm going to factor out the proton mass as well, so that the thing in parentheses is dimensionless. All right, so it's kind of an improvement because it's starting to look closer to this, where it has like a rho total KT over mass, or the mass of the proton, but here it's kind of dividing by a single number, whereas here I'm kind of multiplying by this mess. Well, I can essentially define a new variable such that it does look nice. So essentially I can make this, I can claim that then this is rho KT, rho total, I'll stop writing the T's for total, times mu MP. Where if I want to define that as a definition of mu, then that says that 1 over mu is the same thing as X sub n over 28 plus X sub O over 32, which ends up being about 0.8, which then implies that mu is about 1 1/4. Is that right? That seems too low. Oh, nope, I'm looking at the wrong problem. I'm looking at the next problem that we're going to do. I was going to say, should be somewhere between 28 and 32. And indeed it is. So it ends up being, apologies for that this ends up being 0.0347, which implies that mu is equal to 28.8. There we go. This is what's called the mean molecular weight. It is, in a sense, an average mass per particle. And we can define it just as I did above. So notice that the full definition for a mixed composition is 1 over mu can be defined as the sum of the mass fractions divided by the atomic numbers, the dimensionless atomic numbers. It's worth a highlight. Now notice for the mass fractions, I didn't say this explicitly, but I think it makes sense that the mass fractions, when you add them all up, better add up to 1. Else that means you're forgetting something. Or if it's greater than 1, you're overcounting something. So in this case, this kind of gives you an average mass per particle. In this case, for air, the atmosphere, I could use the ideal gas law now. I can talk about the ideal gas law of the atmosphere just by writing it as kind of rho kT, and then I divide by 28.8 the mass of the proton, rather than having to think of multiple species and all that stuff. So then, the other example I was going to do, and was accidentally copying that answer, is the composition of the sun. Right, the sun. The way astronomy works is that the Big Bang created a lot of hydrogen and helium, and that is most of the universe. Everything beyond hydrogen and helium comes in very, very small amounts. So the sun ends up being 74% hydrogen, 24% helium, and 2% everything else. And we colloquially call everything else metals. Well, it's not just colloquial. There are reasons of calling it metals. So the joke is that the periodic table for astronomy is very simple. There's essentially only 3 elements: H, helium, and then metals, which is everything else, which comes in very small amounts. Such that, so for the atomic numbers, it's 1 for hydrogen, 4 for helium. And when you actually look at the detailed composition, which you will do on the extension, I think this turns out to be something like 20. When you take into account, like this, it's mostly carbon, nitrogen, and oxygen, but then there's lots of other, pinches of other elements too. So then, the mean molecular weight for the sun is then 1 over mu sun is going to be, looks like it's 0.74 divided by 1 plus 0.24 divided by 4 plus 0.02 divided by 20. This is equal to 0.8, which then implies that mu for the sun is about 1.25. As the mean, the mass, the average particle has a mass that's a little bit more than hydrogen, which makes sense since 75% of the mass, roughly, is hydrogen. So the average mass is going to be closer to hydrogen's mass. If you want just one more quick example, let's just take, if you have something that is 50% hydrogen and 50% helium, then the mean molecular weight is going to be 0.5 divided by 1 plus 0.5 divided by 4. That's the same thing as 1/2 plus 1/8. That's the same thing as 5/8. So in this case then, mu is equal to 8/5. Or I guess it's excuse me, so that the mean molecular weight in this case is about 1.8, which is less than 2, notice. So you might have thought that maybe the average was supposed to be 2, because hydrogen has 1 proton and helium has 4, and that there's half of helium and half of hydrogen. But here's where you have to be careful, the distinction. Half of the mass is in hydrogen, and half of the mass is in helium, so then the average mass per particle ends up being 1.8 times the mass of the proton. If I told you the number fraction was 50% by number hydrogen and 50% by number helium, then the average mass per particle would be 2 protons. But it turns out, and I think you actually do this in the extension, that you can, so there is mass fractions and then there are also number fractions, right? So in this case, kind of the mass fractions for hydrogen is 0.5, mass fraction for helium ends up being 0.5. Turns out if you were to compute the number fraction, so use capital N for hydrogen and capital N for helium, ends up being that 4/5 of the particles are hydrogen and 1/5 of the particles are helium. And you're going to try to work it out for yourself. Just use simple numbers, 4 hydrogens and 1 helium. You can show that the average mass is indeed 1.8. So you'll explore that in the extension, doing some other examples. And then also in the extension, you'll include ionization. That ionization releases electrons, which then are additional things bouncing around, which can run into things. So you'll generalize the formula that I've highlighted there. All right, one quick thing I'll say, and then we'll be done, is to remember that pressure is not a vector. So there's a lot of confusion, I think, that gets created when people just blindly say kind of the force is equal to pressure times area, because pressure is force over area. That's not really what's going on. The pressure in this room is not a vector. It is uniform. The pressure in this room, so essentially the particles are randomly moving in all directions. So if I were to put, like the walls of our box, if I were to put like a little sensor, it wouldn't matter which direction, where in the room or kind of what angle it's positioned in the room, it would measure the same pressure just because of the kind of uniformity of what's going on. So what you really need to experience pressure is a pressure gradient. So pressure forces arise from gradients instead. And the thing that I think, the kind of simple example is, here's how to do it. Here's how to think about this incorrectly. So you could say that the pressure of air is about 10 to the 5 pascals at sea level. And if I think of what is the pressure on the outside of my cheeks, what is the pressure on my face? So if I want to calculate the force, on my face, which really I'm going to do my cheeks, then I might, at first attempt think that, okay, well, I need to calculate the pressure of air, which I know, and then I'll multiply that by the area of my cheeks. Or I'll compute the area of one of them and then multiply by 2. So I could get a ruler out. It's about half, I would say, estimate. It's about 6 inches by 6 inches. So I might say that the area of my cheeks, or 2 times the area of one cheek, ends up being about 0.05 meters squared, which then would imply that the force on my cheeks is P air times 0.05 meters squared, which ends up being about 5,000 newtons. So is there really 5,000 newtons of force pushing on my face? You would think then my cheeks are going to get kind of, my face would kind of like implode in, or, as if I'm sucking in my cheeks. Well, that's exactly, why this kind of, this kind of reasoning is wrong. If I have, can't really draw cheeks, I guess. Here's my lips. God, this looks terrifying, right? And so that if these are my cheeks, there's kind of the pressure from the air kind of pushing on the outside, but then there's also air inside my mouth. So then there's also a pressure, from the air pushing on the inside of my cheeks, and they are, in a sense, canceling each other out. The collisions that are hitting the outside of my cheeks are essentially being balanced by the collisions hitting the inside of my cheek. And so I do not feel my cheeks kind of going anywhere or getting stretched or pulled or whatnot. Which can be, sometimes this can be a little bit non-intuitive because you essentially need there to be a difference in the pressure in order for you to experience this force to an extreme. You know, if the pressure becomes too extreme, then, right, it might literally compress, right, your skin or your bones or your, you know, or whatever. But you need very, very high pressures in order to accomplish that. So what you do need instead, right, if you instead say, close your mouth and then try to exhale so that that air from your lungs is then filling up your mouth. There's more particles now in your mouth, so the pressure in your mouth is different than what's outside. So if you kind of exhale, kind of with mouth closed and not through your nose, then right here's the lips. Then inside you have more air inside your mouth compared to the air on the outside. And therefore, the pressure pushing inward is not as great as the pressure that is pushing outward by the ideal gas law. And so there's an imbalance and your cheeks puff out. Unsurprisingly. In that case, the pressure kind of pushes your cheeks out. Just like how blowing up a balloon, the pressure inside is pushing the balloon out. In that case, it's kind of in equilibrium with the surface tension of the, you know, the latex balloon or whatever it is that's trying to contract. Same thing with a suction cup. You know, if this is the wall, you know, how does a suction cup work? You push a suction cup up against the wall. You know, what you're doing is you're pushing out the air from beneath the suction cup. So as a result, there's not a true vacuum, but there's less air kind of on the inside of the suction cup compared to the air on the outside of the suction cup. And so in this case, then, there's a stronger pressure pushing the suction cup against the wall versus the air on the inside that's trying to push it off the wall. And so therefore, what's happening is some friction plus just the air in the room is holding the suction cup up against the wall. Which is why you always want to get, a good seal, right, when they say, suction cups. Because if air can slip back in, then there would be the same amount of pressure on both sides and the suction cup would not work. So in general, kind of the force from pressure goes from high to low pressure. Goes from high P to low P. So if you have some derivative, in one dimension, right, dp by dx, right, it's the negative derivative, to give you the direction. E equals the force. Or more generally, the force due to pressure is equal to negative the gradient of the pressure expression. So if you have some scalar expression for the pressure, you can take the gradient, which might be a function of position, like the pressure in our atmosphere changes as you increase altitude. You can calculate the pressure force as this kind of change. All right. That's pressure plus sum from the lost lecture.